Hello, my name is Justin Castillo, and this is my submission for programming assignment 2. So to get into the program here, at the top we define our quantum. We define a struct that will represent each process. We get all the stats. We have a unique name for the process as well as the index to retrieve it from the array where it'll live uh, during this program. So this is an error handling helper. This is just to make unique names for each of the processes um, with the P and then whatever index is passed in, which will be one bit, starting with 1, which will be defined later. This is the comparator, which sorts by arrival time if the arrival times are not equal. If they are equal, it sorts by first in, first out. Getting into main, so we handle the case where a file is passed on the command line, open it in read mode, and we read n at the top of the file, and if there's no passed, we just prompt the user to enter n at the command line. This is the array that keeps all of the process structs, so we allocate memory for that, all the while guarding against any errors and exiting the program by calling die if there is an error at any point there. Reading the file, we go line by line. So first we consume the rest of the line where n was, which should be the first line. There should be n lines after that to represent n processes. Um, so we assign an index to the process. We make a permanent, we make a process ID that's one based for each process, that's unique for each process. Initialize all of the fields in the struct, and then and then this is what actually gets each line, and we enclose that inside of a guard in case the number of lines doesn't match n at the top. So we use this to iterate through the line character by character. Um, this skips over the leading white space, and then if the line is only white space, then it may be that there are the correct number of processes that are in the file, but we need to skip over a line and then have I kind of reset to the previous iteration so it doesn't stop before it reads the last line at the bottom, the last process on the bottom. So this basically just skips over if it's written like P1 and then arrival burst time. It skips over P1. It skips over and then it skips over the spaces after P1, and then we read the burst times and arrival times into the fields for the current process, and then we close the file. And then this is if there is no file, then we simply do sort of the same thing, but without all of the file handling business, letting the user directly enter arrival and burst time, integer space integer for each line, for each process. So qsort uses the comparator defined above to sort procs by either arrival time or breaking ties with first and first out. So that's all sorted before we even get to the algorithms, right? So this is first come, first serve. We initialize our Gantt chart, which is just a string, set time to 0, and then if there's a gap between the current time and the next and this process's arrival, then we advance time to the process's arrival, and this just handles like if it's at the beginning of the file, then don't print the arrow. If there is something inside the Gantt chart, then print the arrow. Printing the arrow would be appropriate. Okay, so we get the completion time, the turnaround time based on the completion time, and then the waiting time based on the turnaround time. We add those to the totals for first come, first serve, and then this is the thing that actually advances us through the CPU cycles. So we advance time to the completion time of the current process because it's non-preemptive. There's no need to make it any more complicated than that. And then we add an arrow in the process ID on the Gantt chart appropriately. And then we compute the stats and print the stats. We're done with first come, first serve. For round robin, first we get rid of all the old completion times and initialize all of the remaining times to each one's burst time. And we'll subtract from remaining as we go through this. So we could clear our Gantt chart string. We initialize our ready queue, allocate memory for it. We get the front, rear, and the total count inside the ready queue index. And the next index is what retrieves the process from procs. So if the next process to be unqueued is after time equals 0, which is time is 0 right now, then we advance time to that process's arrival. And then we unqueue any processes basically that have arrived simultaneously with the first process. And I should have put this inside of a function. This is the unqueue logic. Basically, any processes that have arrived before or at the current time, put them in the rear of the queue, advance the rear marker, and then add to the count, and then increment the next index in the procs array. So we're cycling until all processes are finished. If the ready queue is empty, then we jump time to the arrival time of the first process and put idle in the Gantt chart. And if there are still some processes that have not been unqueued or touched at all by the current time, then we unqueue those, and we unqueue the ones that have arrival times before the current time. And then we continue this so that this logic doesn't repeat for each iteration of the while loop. This one basically has the index of the process in procs that is next to be executed, or that is currently being executed. And then this is the sort of our simulation of it actually executing, where we move the marker front over and then we decrease the count. So we basically removed it from the queue and have a new front of the queue now. So this is just putting the ID into the Gantt chart, putting an arrow if it's not the first, the first process. And then this branch, there's an if else here. So this branch is if the remaining time is greater than the quantum, and then this is if the process will execute by the time within the quantum, right? So if it's greater than the quantum, we advance time by a quantum amount, which is 2 in this case, and then we subtract quantum from the remaining time in that process. And then since we advance the time, we always unqueue anything that has arrived during that time span. And then after everything that has arrived, we then unqueue the process that has not finished executing, and we reflect that and count the total processes because we're re-adding that process. And then if the process is going to finish, which all processes will eventually reach this branch, then we advance time by either 1 or the quantum. We record remaining just for completeness. It's not really necessary because we don't unqueue the same process again like we do in the other branch, which is the main differentiator between these two branches. We get the turnaround, the waiting time, add to the totals, and unqueue any processes that have arrived by the current time. We free the queue, we get the totals, and then we free the procs array. So let's go ahead and run it. Let's see. Okay, and that is exactly what I expected. Now I'll go ahead and use this file to kind of simulate some wacky input there. Let's see. All right, and that's exactly what I expected. And then we have another test file. And let's see. There's no errors. There's nothing. Executes nice and clean. All right, so to reflect on the efficiency of these algorithms, so we can see that for this first run, the processes are sort of evenly spaced, 0, 2, 4. This favors first come, first serve, since there's no real need to break them up because the arrival times kind of stagger uh, their execution time in a way that's fine for first come, first serve. And it's just 1, 2, 3, and then this one breaks it up unnecessarily, which causes a little bit more inefficiency. For this one, the processes are kind of bunched together. They arrive, 6, 6. Yeah, so round robin is better for when the burst times are sort of uneven. And I'm sorry, that's actually true in this file, where they all kind of arrive around the same point, 5, 5, 3, 3, 9, 7. So we can see that round robin beats out first come, first serve slightly. And then for this file, they are staggered. So first come, first serve wins for this file. Okay, so if we want to try with different quantums, we'll go ahead and make it, let's say 100, and it should be equal to the first come, first serve, right? So let's see. So let's do make clean, and then 3, and then 0, 5, 2, 3, 4, 1. And so we can see they are exactly the same. So if the quantum is too large, then it will devolve into first come, first serve. Round robin will devolve into first come, first serve. Okay, so yeah, figuring out the round robin was definitely harder than figuring out first come, first serve. There's basically 3 different arrays going on here. One of them is just a simple string array for the Gantt chart, and then one is procs, which is the most important one, which has all of the process structs in there. And then the ready queue is a circular queue, and I kind of had a breakthrough. Like I kept visualizing like the first one popping off, the second, and the last one popping off. But it's more like this, like the front keeps moving, the rear keeps moving, it kind of moves, and then the indexes kind of like circle around as it moves. I don't know. I visualized it like that. So yeah, I use GPT to kind of get context for everything and to debug everything, and then explain all of the theory behind it. Give me suggestions for which queues to use, and guard against certain errors. There's a lot of like error guarding, so it's like yeah. What else? I think that should do it. All right. Well, thank you for watching.